Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Tuomas Laakkonen, who will tell us about any Clifford+T circuit can be controlled with constant T-def overhead. And Thomas is a PhD student at MIT with research interests including fault-tolerant quantum circuit optimization and quantum algorithms for differential equations. Previously, he was a research scientist at Quantinuum, working on quantum algorithms for approximating topological invariance. He got his master's in University of Oxford, studying the connection between tensor network methods and complexity theory. So Thomas, the floor is yours.
Hey, thanks. So I'm going to be talking about this paper that you can find on the archive. Any Clifford+T circuit can be controlled with constant T-depth overhead. It's joint work with Isaac Kim from UC Davis. And so the kind of central motivation for this was thinking about how will large-scale quantum computers work. Large-scale quantum computers will almost certainly involve some kind of encoded computation through some kind of error correcting code. And when you are representing a computation in a code, you need to choose some particular gate set that you want to represent it in. And a popular choice for that is the so-called Clifford+T gate set. So I've just shown a random example here of a Clifford+T circuit. You can see there's some of the Clifford gates, which are these CNOTs and Hadamard and S gates on the left and right hand sides, and then some stuff in the middle is Toffoli gates, and this is the +T part. So this example is like a comparison circuit, something you might find in Shor's algorithm, for instance. And many of the proposed error correcting codes that we might use to implement like a large scale quantum computer, like the surface code or the bivariate bicycle code, these can all implement Clifford operations fault tolerantly, which is a good property, but not necessarily the T-gate. And we need both of those things in order to be able to do big computations like for Shor's algorithm. And so I've given here's a figure from IBM's recent work on the bivariate bicycle code. And so like you can see on the right, there's this big circuit with like 3 groups of qubits, and these all the operations that occur on this right-hand side are all Clifford operations because that's what the code can support. And so how do you implement this T-gate, the one that you need in order to be able to do general computations? So one way to do this is called magic state injection. And the idea is that if you want to implement this T-gate on the left, you can instead prepare a magic state, which I'll call the T state, and use only Clifford operations and measurements in order to perform the T-gate on the left using just the magic state on the right. And you can see if you have the magic state on an ancilla, you can perform a CNOT gate from the qubit where you want the T-gate to be onto the ancilla, and then measure it, and then apply some correction. And that correction is also a Clifford gate. But in order for our large-scale quantum computer to be competitive with classical algorithms, we really want to parallelize stuff as much as possible. You know, a lot of quantum algorithms, especially like Grover's algorithm, are like inherently serial, and so they can be very slow. Whereas classical methods, while asymptotically worse than the corresponding quantum algorithms, can often be, exploit parallelism, especially like really big supercomputers are not very fast, although they are they have individually fast processors, but mostly they just have loads of cores. And this is something that's not easy to do quantumly. So we would like to parallelize stuff as much as possible in order to try and be as competitive as we can. But these kind of measure and correct operations that you need to do in order to implement magic state injection are an obstacle to doing this parallelization. And so the first thing to note is that if we were just doing Clifford operations, and if you had arbitrarily many qubits that you can just use as many as you want, then you can actually arbitrarily parallelize your quantum computation. So if you have some circuit, like on the left, I want to do A, and then B, and then C, and then D, and then E, I could actually rewrite this as the circuit on the right, where I'm doing A, B, C, D, and E, but all in parallel. And I have some Bell states that I'm preparing and Bell measurements that I'm doing, before and after them. but I can compress this like 5-step computation down to 3 steps. And no matter how many steps I have on the left, I'll always have these 3 steps on the right. And so if you have arbitrarily many qubits, you can always do this, but only for Clifford operations. And of course, if you want to prepare a lot of magic states for your injections, you can also do that in parallel, right? Because you can just do it independently many times. But the problem really is actually doing the injection of the magic states. And to see why that is, I'm going to consider a very simple example here. I have a T gate and then a Hadamard gate and then another T gate. And if I want to, I can rewrite it, the kind of top line on the right, to say, all right, I'm going to do this magic state injection process twice. And if I do some simplifications here, like trying to parallelize stuff as much as possible, the problem we'll always end up with, no matter how you do it, you always end up with this problem of you have this square root x gate, or it might be an s or something, but there is some gate that is dependent on the measurement result of the first measurement, but influences the choice of basis for the second measurement. And these are like inherently a serial thing. Like I cannot do the second measurement until I've done the first measurement because I can't choose which basis I'm measuring in until I've done the first measurement. And this, no matter how you rewrite this, you always have this problem. And these measurements are inherently serial. So one thing that we know we can do in parallel is if we have T gates in parallel, like I have some qubits and I have one T gate on each of them in parallel, then I can inject all of those in parallel. I can do all the measurements in parallel and all the corrections in parallel. And so one quantity that we might like to optimize about our circuit is called T depth. That is, if I were to write my circuit as a sequence of layers where I have, the empty boxes just refer to like some arbitrary Clifford computation, and then I have a layer of T gates, and then some more arbitrary Clifford computation, and another layer of T gates. The T depth is counting how many layers there are. And there are a few kind of almost canonical examples of computations with high T depth. And one is implementing small angle rotations, which is something that you would do often, for instance, maybe in Hamiltonian simulation. And you can do that with the Solovay-Kitaev algorithm, which is very conceptually neat, but the circuits you end up with have a T depth that kind of is as high as it could be. And the second kind of obvious example of something with high T depth is when you have a unitary and you want to add a control to that unitary, which is also a common operation, for instance, in quantum signal processing. And the quantum singular value transform in particular. So we're going to look at both of these and show that in both cases, you can find something better than the kind of obvious implementation. And specifically, we're going to show 3 things, and they're both the two applications I just mentioned are both going to be built off of this first theorem that we'll show. And the idea is if we restrict only to considering the case of CNOT circuits, so circuits using only CNOT gates, then the controlled version of any n-qubit CNOT circuit can be implemented in T depth at most 36. So like a constant, using no ancillas. Or if we're going to, if we're allowed to use ancillas and measurements, then we can do it in T depth exactly 1. So we can parallelize it as much as possible. And moreover, the T count when we do this, so like how many T gates we use, is not that much worse than what we started with. It's always within a constant factor of optimal. And this might be somewhat surprising because, like, if you have an arbitrary CNOT circuit with just as many CNOT gates as you like, it's known that you can always rewrite this into a normal form, which has at most O of n squared gates. And so if I was going to do the naive thing of controlling every gate, this would give you a T depth of O of n squared over log n. And yeah, we can do much better than that, all the way down to a constant. So I'm not going to talk about how to achieve that T depth at most 36 using no ancillas today. It's a bit more technical. You can find it in the paper though. So today I'm just going to give kind of a sketch of the second one here about T depth exactly 1 using ancillas and measurements.
Sorry, can I just interrupt? I'm just curious, like, is there anything special about the number 36?
No, it's 3 times 12 because I write everything in terms of Toffoli gates, and then each Toffoli gate can be done in T depth 3 without ancillas. And the 12, yeah, I mean that you can explain exactly why, but like this can all be optimized a little bit. I wouldn't say these are like hard numbers. And
Okay.
certainly what I'll show on the next slide are definitely not hard numbers.
Right.
Yeah, so we use this like controlled CNOT circuit construction to show two things. The first one, and I think maybe more interesting one, is that if you prepare this universal catalyst state, that like if I want to implement a small angle rotation up to precision epsilon, I can prepare a catalyst state of size like big of log 1 over epsilon, and then I can use that to implement that z rotation in t depth exactly 1, so as parallel as possible. And this kind of means that from the point of view of t-depth, there's no difference between doing one t-gate and doing any z rotation. Like a t-gate is just a z rotation by pi over 4. Yeah, they're kind of the same from this perspective. And what's nice is because it's universal, like you can prepare this catalyst state once, and it works for any angle that you want to rotate by. It's not specific to the angle or anything. So that's the first thing we're going to show. And then the second application is that we can generalize from CNOT circuits all the way to any Clifford+T circuit. And what we can do with this is if you start out with a Clifford+T circuit with t-depth d, say, then you can implement its controlled version with t-depth that is linear in d. Specifically, the number I've got here is 144d plus 280. But don't take that number seriously. That's just, there's loads of little things that could be optimized in the construction. And even when preparing these slides, I found a few more. So it's not certainly not set in stone. Yeah, so I think first I'm just going to give a bit more background about CNOT circuits specifically, since we're going to be talking about them so much. So yeah, CNOT circuits composed of only these CNOT gates, which have a control and a target. Like I've got this example on the left with 3 gates. And the effect of a CNOT gate is, also called a linear reversible circuit, is to apply a linear transformation to the input bit string that you're applying to unitary. So if I have like this circuit on the left, let's call it implements a unitary, let's say UA, then I can associate that to a matrix, the parity matrix on the right, which I'll call A, which is always an invertible matrix. It's always a binary matrix. And the effect of applying this unitary UA to some ket x is to give you ket AX. So it's like applying a linear operation to x. And these parity matrices have some nice properties. So like row and column operations on the matrix correspond to applying CNOT gates in the circuit. If I compose unitaries in series, like by multiplying them, that is the same as multiplying the parity matrices. If I were to take the tensor sum of, the tensor product of unitaries, this is the direct sum of the parity matrices, so they completely characterize a CMOS circuit. And so I'm going to show this construction of how to do a controlled CNOT circuit in t-depth 1. And so we suppose we're given a parity matrix A, and we want to implement this transformation that takes ket A and X to A and either capital A to the X or just X, depending on the value of the control qubit, which is A. And so to do that, I'm going to define a bigger matrix D, which is just a block matrix where top left block is the identity and the bottom right block is just the parity matrix A that we want to implement. And now we can build up a circuit incrementally and see kind of how the circuit works, or like how the whole circuit will work. So if we start with like the target register we have, X, and some ancillas, which I'll initialize as all zeros, and we apply this UD operation, then this will act on the bit strings linearly. And what we'll get out is the top register, the input register, won't change, and the bottom register will get A plus I times X. Oh, sorry, I made a typo here, but this is ultimately what we want to end up with. And so once we've done this, we can then apply another CNOT gate from all of the ancillas onto all of the inputs. And this has the effect of like adding these two things together. So I'll add A plus IX to X, and I'll get just AX on the target register, and I'll get this A plus I times X on the ancillas. And so now if we were just trying to implement UA, which we could have done another way, but let's pretend we couldn't, then we've got the correct output here, right? We've got AX, but we have some unwanted ancillas, A plus I times X. And so how can we get rid of them? Well, one thing we can do is we can just measure them in the X basis. And this will give you a totally random measurement outcome. But it will, it will successfully get rid of all that unwanted information on the ancillas, and we'll just be left with 0 on the ancillas again, which is nice. But in exchange, we get a phase on the unitary as a whole, and that phase will be determined by the value of x and also our parity matrix A and the measurement outcome M. So the phase depends on the measurement. And we can't just ignore this phase because it depends on the measurement. If we were to ignore the phase, then if we did this computation in superposition, then these phases could cause unwanted cancellation, which, yeah, would not implement the unitary we want. So what we can do is we can do some operation to our measurement outcomes. Exactly what is kind of irrelevant. And we can use this to apply some Z gates to our target. And what this will do is it will introduce another phase which perfectly cancels the phase that we got from the measurement. And that will leave us with just AX on the output, which is what we wanted. So this technique is called measurement based on computations, kind of popularized about 5 years ago by Craig Gidney, which it's very cool. But so far this isn't very interesting because we just implemented like UA without a control, but we want to have a control. So what we can do is take one step back and kind of imagine that we went back to this step with the phase, and now we can add a control to just this CNOT gate in the middle, which is actually like a bunch of CNOT gates from every ancilla to every target. And they're all controlled by the same control qubit, which is in the state A. And this has the effect of if we don't do this gate, like if the control is off, then actually nothing happens to our input register. So we end up with just X. And if we do the gate, then we have the circuit we saw before, and so we get AX. And so this is exactly doing the operation we want, where we take A and ket X, and we get A and X times the controlled version of the CNOT circuit. We still have this nasty phase here, though, and if we try and do the same correction that we did before, it's not going to work. We have the correct basis vectors on the outputs, but we get the wrong phases. So we want to find a correction that actually does work. And it turns out there is one. I won't give all the details here, but you can find the derivation in the paper. It's not super complicated. And the idea is by picking, you can, given the measurement outcomes M, say, you can pick some V and U, which do not depend on X, such that if I do some Z gates and controlled Z gates on the input register, they will perfectly cancel out that unwanted phase that we had. So this is kind of almost what we want. We can see that the only non-Clifford operation in this circuit, which is the thing we care about the t-depth of, is this one Toffoli gate right in the middle. And this is really like a bunch of Toffolis from every ancilla to every qubit of the input. These are not yet parallelized because they all share one control qubit, but we can parallelize them. You get a slightly bigger and maybe more impressive looking circuit where I've just expanded all of these registers to show every individual qubit. So I have now, instead of just one input X, I have a whole bunch of inputs X. And what we can do is we can introduce even more ancillas here, and we can kind of fan out the control qubit onto these extra ones and use that to parallelize all of these Toffoli gates. And so now we have like an implementation of a controlled CNOT circuit, but the only non-Clifford operations are these Toffolis that are highlighted in gray, and all of these can be implemented in t-depth exactly 1, and they're all in parallel. So the whole thing is t-depth exactly 1. And we discussed before that like the measurements not being parallel for t-state injections was like the obstacle that we wanted to get around. And here we can see that all of these corrections that we get from the measurement based on computation, you can also do these all in parallel using the fan out of the control qubit. So we've succeeded in the goal in that it has t-depth exactly 1, and also all of the measurements are parallelizable. And so we don't have any issues with what we saw before. Okay. So yeah, from this we can get to our applications that I showed before. And so yeah, the first one I'll talk about is these catalytic Z rotations. And the whole idea of catalysis is basically like the very classic concept of phase kickback, So imagine I have some unitary u along with an eigenvector psi, and that eigenvector has eigenvalue e to the I alpha. Then if I prepare an ancilla with the psi state, the eigenvector, and I apply a controlled version of this u to the ancilla with psi, because psi is an eigenvector, that's like it's the same as if you had done nothing to the actual ancilla qubit, but you had rotated the control qubit through alpha, the eigenvalue. And this is exactly phase kickback that you might see in the quantum Fourier transform, for instance. And so if we're more interested in implementing a small angle rotation RZ alpha, like if we wanted to do Hamiltonian simulation or something, then one way to do this, like we could do this with the Solovay-Kitaev method, but you could also find some u and psi so that this is true, and you could implement it that way instead. And this would be particularly beneficial in our scenario if we know that controlled u has low t depth, and we know that psi is easy enough to prepare, and also that like u of psi at least approximately has the right eigenvalue. So if we could, given some alpha, we could satisfy all three of these conditions, then we could implement RZ of alpha, at least approximately, in low t depth. And it would be nice if that approximation could be arbitrarily good. And the important and useful part about this is that when you do this catalysis procedure with the phase kickback, you don't use up this psi state. You get to keep it, and so you can reuse it. And if you want to apply many small angle rotations, which often you do, especially in the like Hamiltonian simulation example, then you can reuse it many times, and you only have to pay the cost of preparing it once. And so as long as it's like at least moderately easy to prepare, then that's not so bad. Okay. So yeah, I mean, as I kind of hinted at before, we would like it if controlled U is low T depth. And we've just identified, a whole family of circuits with low T depth, which is controlled CNOT circuits. And so yeah, we're looking for U and psi that satisfy this equation. And because, the first theorem we proved, we would really like U to be a CNOT circuit. And so what we can do is, it's fairly easy to prove, just like some algebra. You can kind of characterize all of the eigenvectors of CNOT circuits. So if I have a CNOT circuit UA with parity matrix A, then the eigenvectors depend on the period of A. So like if A to the P is the identity, and then P is the period, and P is the smallest integer of where this is true. And because we're working with binary matrices, or parity matrices or binary matrices, then you always have a finite period, which is not the case for like if you had integer matrices, right? But if you know the period of A, which is something you can calculate, then you can write down explicitly these eigenvectors psi k. And these are like a sum over powers of A applied to some vector V. V you can also calculate. I haven't given a definition here, but it's not so it's pretty easy to do. It's certainly something you can calculate classically. And the eigenvalues are defined in terms of this what I'm calling tilde omega, which is 2 pi I over p. So there's a whole family of eigenvectors, psi k, and each of their eigenvalues is omega tilde to the k. So like if you have a matrix with really high periods, each of these eigenvectors will catalyze a rotation that is some fraction k over p of the whole unit circle. And so if p is very large, then these rotations can be very small. And so you could like arbitrarily well approximate any rotation that you like. And more generally, if I have like a to the power of j, then that will have eigenvalues that are just powers of the original eigenvalues, kind of obviously. Right. And so, yeah, as I said, we would like to find a matrix which satisfies these properties in that it has a very high period. And there do exist matrices with this property. The maximal period is 2 to the n minus 1 if you have an n by n matrix, and you can indeed find a matrix which satisfies this. This comes from the theory of finite fields. You can do this. And so like the whole procedure that we have is, suppose we want to approximate some rotation by an angle alpha up to precision epsilon, then I can pick number of qubits n that goes like log 1 over epsilon, which is kind of as good as we could hope for. And I can pick any k that is co-prime to 2 to the n minus 1, so it doesn't share any common factors. And then for any angle alpha, we can find some integer d so that omega tilde to the d is approximately e to the I alpha, at least up to our precision epsilon. And then by picking basically the dth power of an, multiplied by some extra factor k inverse, which is just to cancel out the effect of k, but we can come up with a CNOT circuit such that the eigenvector psi k has eigenvalue omega tilde to the d, which is approximately e to the I alpha. And since that is a CNOT circuit, we know we can implement the controlled version with t-depth 1, which is exactly what we wanted. And so we can approximately implement a z rotation by any angle alpha in t-depth exactly 1 as well. And yeah, what's interesting to note is that psi k actually doesn't depend on alpha at all, right? Only the CNOT circuit that we use to do the catalysis, which is an to the d essentially, depends on alpha. And so we can prepare this psi k once. We can use it for any value of alpha that we care about anywhere in our circuit, which is a nice property that is not true of some other methods that I'll discuss in just a second. Yeah, so there are other ways to do this kind of thing where you want to implement a small angle rotation in Clifford+T. And the first thing to note that I think is often not talked about and is quite significant to my mind is that if you have a circuit with, say, k rotation gates, and you want to implement the whole circuit to precision epsilon, then you need to implement each of those rotations to a precision epsilon over k. And so if you do something like Solovay-Kitaev, which has like a logarithmic overhead in 1 over epsilon, then actually now the overhead you have will depend on the size of your circuit, right? Because you've replaced epsilon with epsilon over k. And so the total number of like T gates you would need, instead of going like k times log 1 over epsilon, actually goes like k times log k over epsilon. So now it goes like k log k, right? It's a nonlinear overhead in both T count and T depth. But luckily, our method is like the t-depth is independent of the precision, right? It's always exactly 1. The only thing that differs is how many ancillas you need. And so it's like asymptotically better. And so here's a couple of different options that you could use. So there's like classic Solovay-Kitaev. We have this overhead that goes like log to the 4k over epsilon. People have optimized this for the specific case of Clifford+T. This paper from Peter Selinger and Neil Julian Ross is like you can get it all the way down to like the constant factor is 3, and there's now no power on the log, which is nice. But this is still like nonlinear. Yeah, there are other catalysis methods not similar to the one I've just shown you that also comes from Craig Gidney, I think. And that is based on these like phase gradient states, and the catalysis circuit becomes an addition circuit, and we know how to do addition circuits in like very shallow, but still not constant depth. So what you end up with something like k times log k over epsilon, which is better, but still not perfect. But actually, this method with the controlled CNOT circuits, you can get down to a constant T depth, and that was first realized by my co-author Isaac Kim, and he showed a method with T depth 3, but it was kind of a little bit more difficult because the catalyst states that he needed in his paper, like to prepare them, you actually had to do Shor's algorithm basically. So they were really hard to prepare. And so the one benefit of the method I presented here, although I haven't told you exactly how, but these catalyst states psi k can actually be prepared really easily. You can basically just do phase estimation, and it's quite simple to do. Yeah, and so we can see that like this what I've presented has kind of almost as good as we could hope for in terms of has T depth exactly K. I don't think we could go lower than that. It has some overhead that goes like log K over epsilon, like additive overhead instead of multiplicative. And in terms of T count, it still matches like the best we can get from Ross and Selinger or Solovay-Kitaev, and it's K log K. And it doesn't use too many ancillas either. So yeah, that was our first application to catalytic Z rotations. And the second application is to controlling arbitrary Clifford+T circuits. So as I've mentioned a few times, if we do this like naive method of adding a control to some circuit that has a very high T depth, like I've just given a little example here, like I have some circuit of like 4 or 5 gates, I want to add a control to it, then the naive way to do this is just to add a control to every gate. And that's totally something you can do. But even if we had gates in the circuit that were originally in parallel, they are all now in serial because they all share the same control qubit. And this is kind of unfortunate because we would really like, to parallelize as much as possible. And we can do better than this. And so, yeah, I'm going to show you how to do that for Clifford+T circuits. But first, I'll just talk about Clifford circuits because it's a little bit simpler. So Clifford circuits, we have, they're just circuits made up of the gates only CNOTs, Hadamards, and S gates, square root Z. And a nice property of Clifford circuits is that you can take an arbitrary unitary that was generated by a Clifford circuit and rewrite it into this normal form. So there are a variety of normal forms, but I've shown the one here that is due to Scott Aronson and Gottesman, where it's comprised of a bunch of layers, each of which uses only one type of gate. So we have some layers which are just Hadamards, some layers I've marked C are just CNOTs, some layers are just S gates, and so on. And there's a total of 11 layers here. But because there's like a fixed constant number of layers, it means if I could implement all of these layers in a constant T depth each, then the whole thing would be a constant T depth. And so for any Clifford circuit, we would have a constant T depth. Sorry, I mean, when I control these, if I could implement every controlled version in a constant T depth, sorry. And so we already saw how to do the CNOTs in constant T depth, right? So all of these C layers, we already know how to do. So that's nice. The only thing we need to do is figure out how to control the Hadamard and S layers. And I won't prove this to you, but this isn't too hard to figure out. So for instance, if I have a bunch of S gates in parallel and I want to add a control, I can set up a circuit like this where I have T depth 2. I have 2 layers of T gates and I have a bunch of CNOT gates that are coming from the control qubit to all of the targets. And it's okay that these CNOT gates will share the same control because we don't care about whether our Clifford operations are parallel, not only the T depth. And here the T depth is 2, so that's good. And then we have a similar thing for Hadamard, where we just have basically the same thing again, T depth 2, and some CNOTs onto the targets from the control. And we just surround it with some square root X operations. And from these two, and the fact that we already know how to deal with CNOT circuits, this immediately gets us to saying that the controlled version of any Clifford circuit can be implemented in constant T depth, which is nice. The constant factors are not great here. I mean, like, this choice of normal form, it has a lot of layers. There are alternatives with fewer layers. So like, there's definitely optimization to be done to these constructions, but like it's in its most basic form, we have at least proven that it's constant T depth. I think that constant is 280. Yeah, that's the one I had on one of the earlier slides. So if we want to do Clifford+T circuits, we also need to consider parallel layers of T gates, and this is a bit more complicated. But the basic idea is this. So if we have just one T gate and we added a control to it, we can rewrite it in this seemingly extremely complicated way. And I don't even know how I just got to this circuit by like playing around with the simulator. Like I have no idea why this works, but I know that it does. But you can rewrite it in this kind of extremely complicated way using a few extra ancilla qubits. And the important thing to note is that these ancilla qubits don't have to be initialized in any particular state. This circuit works regardless of the state of the ancillas. And so what we can do is we can apply this to all of the T gates in like that we had in parallel in one layer, and use just like pick any qubits that are not being currently used and use those as our ancilla ones. And we might have to do a couple of different, like might have to split each of our layers into like 4 if there was a T gate on every qubit. If we split that into like 4 groups, then now the 3/4 of the qubits will be unused in each group, and so we'll have 3 that we can borrow to use as our ancillas. And once we've done this, what you may notice about the circuit on the right, I mean, again, the inner workings are impenetrable and also not important, but the circuit on the right only interacts with the control qubit through Clifford gates, specifically CNOT gates. And so if I do this rewrite and then I kind of overlap all of the control T gates in parallel, I will only have I will have everything in parallel except some CNOT gates, and we already discussed that that was fine. So if you do it this way, you will end up with a constant T depth through controlling a layer of T gates in parallel. And this is also where a bunch of these constant factors come from, because this, as you can see, is very long and quite inefficient. But now that we have that, even if it's a bit, inscrutable as to how we came up with it, we can use that to generalize to Clifford+T circuits as a whole. So if we suppose we have some Clifford+T circuit with T depth D, that means we can rewrite it in this layered format where we have some Clifford operations C0, and then a layer of T gates, and then C1, and a layer of T gates, and so on up to CD. Then we can implement the controlled version by only controlling the T gates that lie between the Clifford operations. And what will happen is when the control is active, this will implement the original circuit as you would hope for. But when the control is off, it will implement some random Clifford operation that's the product of C0 through CD. And so by adding the adjoint of that, which is controlled on the opposite state, so like it only is applied when the control is off, that will perfectly cancel out that extra Clifford operation. And I've called this V here. But since V is Clifford, we already know how to do it in constant T depth, so that's fine. And so overall, what we get to is that if we started off with a Clifford+T circuit with T depth D, then the controlled version has T depth that is linear in D, which is nice, and is much better asymptotically than the naive construction. Yeah, so yeah, to come to some conclusions, low T depth constructions would enable the parallelization of quantum computations, like large scale quantum computations, in the regime where you're working in a code that allows this, like the surface code, and where you have arbitrarily many qubits. So kind of long-term, large scale is what I'm thinking. And so we came up with a few specific low T-depth constructions. The first one and most important of which was, despite an arbitrary CNOT circuit being like O of n² gates long, we can come up with a controlled version that could be implemented in constant T-depth, either with or without ancillas, although I didn't show the without ancilla case here. And from that, we got 2 applications, one of which is that if you had any Clifford+T circuit with a low T-depth, then its controlled version also has low T-depth. And if we prepare some reusable catalyst states, we can implement an arbitrary angle Z rotation using one of these controlled CNOT circuit operations, and so in a T-depth exactly 1. And compared to other approaches based on like Solovay-Kitaev or catalysis with phase gradient states, this is almost optimal in terms of T-depth, and is also pretty good in terms of T-count. So that's just what I showed today, but there is some more in the paper. So there is, constructions for controlled CNOT circuits and Clifford circuits using no ancillas. And for those constructions, and actually for all of these constructions, we show that the T count and not just the T depth is approximately optimal. And what that means is it's always within a constant factor of the lowest possible T count circuit you could get for any control Clifford operation. And I think this is quite interesting because generally speaking, optimizing the T count of a circuit, like making it as small as possible, is known to be an NP hard problem. And I think even to approximate this optimum is perhaps known to be hard. And so what we can see is that, like, for this specific case of like Clifford circuits, we can actually, or sorry, not Clifford circuits, but CNOT circuits, we actually get, it's easy to do this optimization, and you can come up with something that's at least approximately optimal. So we also discuss, how to prepare the catalyst states, and yeah, explicit constant factors for stuff. Like, as I said, more optimization to be done, but at least asymptotics, we have. And yeah, that's all I had for you. So thanks. And if you have any questions, feel free to ask.
All right. Thank you very much for a very splendid and cleanly presented talk. Yeah, I think we have plenty of time for questions and discussion. So if anyone in the audience has a comment or some questions, please feel free to unmute and ask them now. All right, maybe I can go first. I'm just curious, like, so does this have any kind of implication to like simulation of circuits? So if I have a classical way to simulate a quantum circuit, like a Clifford+T circuit, does it follow kind of like, oh, then I should be able to also do it for the controlled version, something like that?
So this is an interesting question, actually. Yeah, so this is something I've been thinking about, but I think that, like, these controlled Clifford circuits kind of give you an asymptotic separation between what you can simulate and what you can implement. So you if you had some way of simulating Clifford+T circuit, let's say that there are these stabilizer rank methods where you decompose your circuit into a bunch of a sum of Clifford circuits. Um, all these controlled circuits can always be decomposed into exactly two terms, like two Clifford circuits, because one of them is the identity and the other one is the Clifford circuit itself, right? And so these are trivial to simulate, but you can show that you need at least like O of n T gates to implement them. Whereas if you were just to simulate those O of n T gates on classically, it would be exponential in the number of qubits. So in fact, it turns out that these are easy to simulate and harder to implement than you might expect.
Oh, okay.
Yeah, I think I'm not sure, but are there any trade-off, like if you want to, because you using arbitrary CNOT to reduce the T count,
Mhm.
and I think recently people showing that magic state is constant overhead, like it is from Minshew's paper, and so I was wondering, is this trade-off how to say? So if T count just like constant number of C naught, if your trade-off like able to still provide advantage. Yeah.
Yeah, so in terms of T count, I agree this is fairly weak as an argument because yeah, you're right. Like magic state cultivation and such is very powerful, and yeah, the cost of magic states is presumably much lower than we had previously expected it to be. But in terms of T depth, there's not really much you can do. Like, it doesn't matter how fast you can prepare T states if you are limited by how fast it is to inject them. So if you're in a scenario where measurements are expensive, more expensive than preparing the magic states, then you still really care about this T depth because you want to minimize the overhead of serial injection measurements. So I think it does definitely come into play there, but you're right that it's non-obvious, especially for T count. Like, it probably doesn't help much for T count. Um, one thing that is maybe interesting is that when you have a circuit that looks, yeah, like this is a good example. We have these fan-out circuits where it's a CNOT starting from some control and then is targeted to a bunch of qubits independently. At least in some codes, this operation is cheaper than it would suggest otherwise. Like, I'm not sure about lattice surgery, but I know for if you're doing defect-based computation in the surface code, then this kind of fan-out operation is the same cost as a single CNOT. So if you can write your circuits in terms of these fan-outs, it might actually be not necessarily as expensive as it seems at first.
I see. And start from this part. So I think you mentioned most on surface code. So this method also help like LDPC code or other code form. Yeah.
I don't know. I think there has been some work recently about parallelizing these kind of things for arbitrary LDPC codes. I think very recently, like in the last month. I haven't read that paper though, so I don't actually know the conclusions, but maybe.
Yeah. And yeah, also a final question I think is the rotation part, because I'm doing the quantum simulation, so I'm quite interested in your like almost arbitrary precision. So, but I look at this table, you still have log k over epsilon. So why is this constant? So maybe I'm missing somewhere. Yeah. Like
In the T count or the T depth?
Your both T count and T gate have epsilon, like, or you just neglect the big O part of a T.
So for the T depth, this overhead, like the additive overhead of log k over epsilon, is because you have to prepare the catalyst, and that takes time, log k over epsilon. For the T count, I think it's kind of unavoidable that you end up with something that goes like k log k over epsilon. Yeah, I'm not sure, but I would assume that you can't do better than this just because of the practicalities of approximating like a continuous thing with a finite number of, like with a discrete set of points that you can reach by applying so many T gates. Yeah, I think this would be optimal for the T count, at least asymptotically. The T depth, yeah, I mean, there is an overhead, but that overhead is additive, so it's not so bad. Especially as K increases, it becomes less important. But the idea is that, yeah, this is because of the catalyst preparation.
I see. Yeah, I quite like this idea because I think this is help a lot for quantum simulations. And I also wondering, like, because you're preparing this by the like seeing some like complex trivial like metrics work, is that hard to find this like for like how to say, if I want to simulation any system, is it hard for me to like find this metrics that able to provide me these properties, like to do your catalyst? Or just sorry.
No, sorry, could you repeat that a bit? I'm not sure I quite understand.
Yeah, so okay. So if I want to really doing this like in real implementations, so I need to find, I think you have some constant you need to search, coefficient you need to search, like the matrix A or
I see.
yeah.
This is very easy to do. Yeah, so you need these matrices A, N. Yeah, you can yeah, you could do this easily. You start by picking a polynomial, like a binary polynomial of degree n, and it needs to satisfy some certain properties, but almost picking one, I think picking one at random has a high chance of success, for instance. And then you do need to calculate, this vector v, but you can do that in polynomial time classically. And it's fairly fast in practice. Like, I think you could put n as like 1,000 and it would be doable. So like, epsilon is 2 to the minus 1,000, I think is probably enough precision for anyone. And so, yeah.
But picking at itself is not NP hard, or
no.
Yeah. Okay. No. That's good. Yeah.
Yeah, it's the same as constructing a finite field of order 2 to the n, which I think like people in number theory have methods for doing this. Yeah.
Okay. Yeah. Thank you. I think that's all my questions. Yeah.